Alright, here we are in 5.3. The objective here is to start to work with exponential functions, which we have a little bit when we did the growth and decay models in 1 and 2. Those were exponential functions. Okay, what we've covered so far that wouldn't be counted as a function is all the properties of exponents. Now those can come up all the time with exponential functions, and that's why we learn them. But those by themselves are not functions. Okay, a really common model is doubling time. Okay, a lot of variables that we've seen here before. A sub O, that's our original amount. Y is the new amount. We're going to be using the growth rate of 2 because we're talking about doubling. X is our time. That's our variable for time. But the new element is right here. We throw in D, which is the amount of time it takes to double. For example, if a bank advertises that if you open a savings account that can double your money every 12 years, now they're using some specific terminology here that we should be also using. A sub t is what they're using for y. The exponent would be t over 12. Okay, the exponent would be t over 12, which kind of leads us back to 5.2 when we looked at rational functions. That in a model like this, we can end up with fractions in our exponent. The next piece here says determine the yearly increase. Now this is exponential, so we're talking about rates. So this is going to be as a percentage. Okay, this isn't linear growth, so it's not going to be going up by the same fixed amount every time. But here's how I could do this. Properties of exponents would allow me to take 1/12 and pull that inside the parentheses and keep it with the 2, and I could just leave the t on the outside. Well, if that's the case, out here, this is like t over 1, which would imply that d, the amount of time it would take to double, would be 1. Okay? So there I could get the yearly increase by just, and if it might be, and this is why I think it's tough to see, it might be more helpful to go and look here. Okay? To here and see that if we go that direction, okay, our properties of exponents would tell us we can take 1/12 times t to get t over 12. Okay? The bottom line here is whatever t to the 1/12 power is, which is about 1.059, that would be the model. Excuse me, I said earlier that would be the, this would be the, if it were to double in a year. That's not true. This is still doubling in 12 years. This would be the model, however, if we wanted to look at year by year growth so that it will double in 12 years. Okay, that's what we're looking at here. Yeah, this would no longer apply up here because our base isn't t. Okay, this would not be a doubling time model. We would see with this, however, that it will double in 12 years. Okay, so a little property of exponent allows us to switch that up and to get that model to go year by year. Very similar, we can look at a half-life model. Really the same idea, the only difference is the base of the exponent's a half. Okay, h, what I'm dividing x by in the exponent is still up here. That's still the amount of time, for this case, for something to be cut in half. So we have a radioactive isotope that has a half-life of 5 days. If the original amount, there's A sub O, is 15, how much is left after 12 days? Well, there's my exponential function to represent that situation. I have x over 5, which means the half-life is 5 days. I have 15 in for A sub O, so the original amount is 15 grams, and of course my base of my exponent is half because this is a half-life model. So to answer the next question, how much is left after 12 days? that would simply be a matter of evaluating at x equals 12. Okay, another situation here where it's very important, make sure that that fraction is in parentheses. If you were to fully simplify that, making sure you evaluate the exponent first, you get 2.84. Okay. Now here we're going to do really the same thing we did before. At what rate does the isotope decay each day? I'm going to head back up here, and I've still got 15 as my starting amount, 1/2. But just like before, when I played around with this and pulled the constant part inside, I'm going to do that again. I'm going to leave x out on the outside, and in the exponent, I'm going to pull in 1/5. Okay, so now the amount it's going to decay each day is going to be 1/2 to the 1/5 power. That you need a calculator to evaluate, and it comes out to be 0.87. Okay, now we have to be very clear as to what this number means. This is not saying that we lose 87% of the radioactive material each day. If you think about the problem on a larger scale, that doesn't make sense. If we lose half of the material in 5 days, how on earth would we lose 87% in a day? Okay, remember that when we're talking about decay, if we were to put it in the context of this function, we'd take 1 minus our rate of decay. 1 minus 0.13 is 0.87. Now for this, model to work, okay, the base has to be the amount that's left over. Okay, because what we want this function to tell us is, let's say after 12 days, what is left? What is left of the radioactive material? Okay, so I would have to write it in this form. Okay, this part tells me I'm losing 13% of the material per day, which is much more consistent with losing half of it over 5 days. Okay, but my function, the base I need to use is 0.87. All right, which if I write it this way, I can see what the rate of decay is in the sense of how much material is being lost. Okay, very important to be clear on those two things. Okay, 87 or 0.87 is how much is left after a day, because 0.13 or 13% is what's lost. This is, for the most part, an unrelated little problem, but we do want to practice how to write an exponential model if we have 2 points on our exponential curve. Okay, so here we're not talking about half-lives or, doubling or anything like that. So just the basic form of an exponential function is the starting amount times the growth rate to the x power. Now remember, this 1 represents an x coordinate, the 10 is a y, the 3 is an x, the 40 is a y. So if I plug those numbers in here, what I have is the first one saying that 10 equals the starting amount times the growth rate to the first power. The second one says 40 equals the starting amount times the growth rate to the third power. Now what I have here is 2 equations with 2 variables, which I can solve. Hopefully this situation kind of reminds you of elimination that we looked at earlier this year when we had 2 equations with 2 variables. The difference here is that these are exponential models, not linear. Okay, I'm going to do something really similar. But remember, with linear equations, I added or subtracted the 2 equations to get a variable to cancel. Here, I need to divide. 40 divided by 10 is 4. A sub 0 divided by a sub 0 is 1, which essentially, with an exponential model, we've gotten that variable to cancel. And then b to the third divided by b, there's a property of exponents. That would be b squared. So my growth rate squared is 4, and by taking the square root of both sides, my growth rate, b, is 2. Let's go back to this equation right here. 10 equals the starting amount times 2 to the first power. I could divide both sides by 5 and see that that means the starting amount is 5. Now the directions here are asking me to write a model. So the final answer would be 5 times 2 to the x power is the exponential model that fits those 2 points. So very similar to elimination, except because it's an exponential model, once you set up the 2 equations, divide them. A fun little rule right here. Kind of a random little thing, but it's a helpful little trick that we can use, called the rule of 72. If we have r as the percentage growth per year, we can approximate the doubling time by taking 72 and dividing it by r. Simple example. Let's say the population of Long Lake is growing exponentially at 2%. If that rate continues, how long will it take to double? What this rule says, to get an approximation, and it's worth noting, this is an approximation, it's not a really exact, super scientific type of thing. Just a little shortcut to get an approximation for doubling time, it'll be about 36 years. Okay? Important thing to remember here is when you plug it in, keep it as a percent. Normally when we do operations with percentages, we always switch them to a decimal. Here's a case where we don't. Okay, just leave it as a percent. If you don't, you'll usually get an answer that's pretty unreasonable, that doesn't make any sense. In this case, in really every case, you'll get a number that's way, way too big. Now, just to kind of give you an example of this with the problem that we saw, we started the whole lesson with an example on doubling time. Okay, and we had an example where we saw the rate. Okay, I'm going back to the very first one where we saw that it was the starting amount times 1.059 to the t power. It was the account, the bank account that was doubling every 12 years. Remember, this rate right here implies that the account is going to get 5.9% growth per year. Okay, so what I would do according to this is I would take 72 divided by 5.9, keeping in mind that this model came originally from the doubling model of 2 to the t over 12 power. Okay, and the problem told us that this account doubles every 12 years. We'll take 72 divided by 5.9. We get 12.2. Again, not exactly 12. That's not what this is designed to do. Just a little approximation. Just a little shortcut that we could use if we wanted to, to go from our rate to kind of get an approximation for the doubling time. Well, that's all for 5.3. If you have any questions, make note of those, and let's talk more in class.